lab 11.1, we're going to start looking at the details of an FPGA by looking at some of the most common reporting features that are provided to you in the synthesis tool Quartus. So in this lab, we're not actually going to put any new VHDL on the FPGA, but what we are going to do is look at 5 of the most common reports. And so as we walk through these of where to find these reports and what the results are, the deliverables for this lab will be screenshots of these 5 particular different screens. Okay, so to begin with, we want to create a new lab by copying a prior lab that has a lot of the logic that we want to report on. So what I did in this lab is we want to copy lab 10.2. And this is a memory lab, but the reason that we want to copy this is because it has a whole bunch of different types of logic. So in lab 10.2 we had a memory array that'll be implemented on some of the onboard RAM on the FPGA. You had 7-segment decoders, which are combinational logic, so those will be implemented as in lookup tables. And then we also had a control finite state machine in here, and so we can actually view this logic using the state machine viewer. And then also it just had a couple different processes on here which will get synthesized to stuff. So what we're going to first look at for the first of the 5 deliverables is device utilization. Okay, so if you go into Quartus, I've already copied over the prior lab, and I went ahead and synthesized everything. And the first thing I want to do is look at the resources that my VHDL would use. There's 2 ways to look at it. One is just a generic look at the VHDL after it's been synthesized but not really technology mapped. And what I mean by that is that you can go into analysis and synthesis, and that'll just take a first pass at how many D flip-flops are you going to need? How many memory cells are you going to need? And it doesn't really say what percentage of the Cyclone 5 FPGA we're going to use. It's kind of pre-technology mapping, okay? And so if I come under Analysis and Synthesis and I go View Report, I can double-click on that, and it'll bring up this Analysis and Synthesis summary. And before we look at that, one of the important parts of this to get used to with the flow is that there's one giant report table of contents called the compilation report, and you can see that underneath here there's all these different reports that were generated during the synthesis step. And what happens is that you can find every report by going to the table of contents, but sometimes it's kind of confusing to dive down through these little menus and figure out which one you're looking at. So over here in the task pane, what happens is when you double click on report, it actually just jumps you over to the summary for that particular step. So it's kind of a way to kind of narrow in on what you're trying to look at. Okay, so the first thing we can do is look at the summary, and this just synthesizes the VHDL and looks at it and tells you things like you're going to need 63 registers to implement this design. You're going to need 256 bits of memory and at least 82 pins. Okay, so it took a first step at looking at that. And then if you want to get a little bit more detailed in terms of FPGA usage, you can actually go down and look at the resource usage summary, and this would tell you what it would take in terms of resources if you were on an FPGA. So it comes in here and it starts talking about how many logic modules you'll need if you were going to implement on a Altair FPGA, and it's like it needs 57. If you were going to do a lookup table for combinational logic, you're going to need 13 6-input functions. You need 22 4-input functions. You need 64 that are 3 or less input functions. So you're going to need 63 registers like we saw before, 82 pins, and 256 memory bits. And this is kind of the first pass at saying, okay, just how big is my device? You know, without even picking my FPGA, this will give me an idea of the size of FPGA I would need, okay? All right, so then if we wanted to look at the resource utilization of the Cyclone 5 that we're actually using, which is the 5C EBA 4F23C7, the way we do that is we go down into the fitter step, and when you expand the fitter, place, and route, you see another view report. And when you double click on that, it takes you over to a different part of the compilation report table of contents. And you'll see over here now you have this summary. And this is where you start seeing things like percentages. So for example, if you could look at this logic utilization, it's saying how many of these logic modules are you actually using? Well, of the 18,480, our design only takes 58. Okay, so it's taking less than 1% of the resources with respect to logic utilization. Of the total registers, 74. Okay, not that big of a deal. Of the total pins, we used 37%. So we actually did use a noticeable amount, 82 of 224. For the memory bits that we're going to use, we only used 256 of 3 megs. Okay, so we used hardly any of that. Okay, so this is where you actually start looking, and if you ever got close at this step to running out of room on an FPGA, this is where you would say, you know what, I'm going to switch my FPGA. I'm going to actually choose a different part, and then I would get better utilization. So if I was at like 99% of all my resources, you might be running into some issues where your FPGA is full. So you might want to choose a larger FPGA and then go, and then rerun this and see if you can get your utilization down. Okay, so that's just a high-level utilization report. So your first deliverable is to take a screenshot of this screen right here showing this report and upload that as an image. Okay, the second thing that we want to look at is the timing report. So whenever you do something that's synchronous, one of the benchmark specifications for the system is its maximum clock frequency. And so the Quartus tool will actually take an attempt at modeling what the maximum clock frequency is based upon the overall delay in the FPGA, or of your longest path. So the way you get to that is if you come back over into the task pane, what you see is this step called TimeQuest Timing Analyzer. And if you open that and you double click on TimeQuest Timing Analyzer, it's going to go through and it's going to actually run an analysis on finding the worst case delay in your system. And then what you can do here is you can come in here and you can set up some of the the various settings that you want here. But what is more important is this view report. So after I ran that, it brings up a tool and runs it. But if I come along and I try to do a run report, that shows me kind of the summary of what's going on. Okay, now it has some different models for the transistors on this FPGA. And it'll always give you 4 different models. 2 slows and 2 fasts. And what it's talking about there is whenever you fabricate a transistor, you're going to have a range of tolerances, and on the maximum tolerance you might get the fastest transistor you could possibly get, and then if you're everything is off tolerance, you'll get the slowest. So for those particular slowest and fastest models, then they also give you a model of what it would look like if you had the hottest possible condition, which would be 85C, and the coldest possible condition, which would be 0C. Now, integrated circuits run faster when they're slow. So your absolute worst situation would be you have a slow transistor and it's super hot. So this is where you would say, okay, if I am guaranteed the worst case scenario, this is where I would want to actually look at what my maximum frequency is. So if you click on this, it actually has this report, and it comes into here and it tells you, it looks at your system and says, it first analyzes what are the main clocks. And so it notices right away that you're using this clock 50, which is the 50 megahertz crystal that comes into the FPGA. It noticed right away that you drive a D flip-flop clock with that. So it said, hey, I know this is a clock. Now, in our situation, we actually only use that on 1 clock, but it said based upon the delay in the path from that pin to the first D flip-flop, this could run at 167 megahertz. Okay, so it could run much faster than the crystal is actually running. Then it said, you know what else I noticed? I noticed that you had this clock div, which was the output of our clock precision clock divider, and it was used to drive the D flip-flops of a whole bunch of other circuitry. So the synthesis tool noticed that this was a clock that we're using, so it did all the analysis on that, and it looked at all the delay of the combinational logic from the outputs of D flip-flops to the inputs of D flip-flops, and it determined that we could actually run that internal clock at 210 megahertz. Now, of course, we're not. This has no idea what our circuit is actually doing, but if we wanted to, we could potentially run the clock divider output at 210 megahertz. Okay, of course we're dividing that down to our pre-selected values of like 1K and 100 hertz and stuff like that, but these would be the maximum clock frequencies you could have. Okay, so this is the second deliverable. So if you just take a screenshot of that screen right there, then you will have part 2 of this lab, and then save that screenshot as a JPEG and upload it. Okay, Then the third deliverable that we want to look at that is of interest to us is the RTL view. Now in RTL view, it's interesting because it's the first time you actually get to see a graphical interpretation of your VHDL. You know, we design our VHDL and we're always just typing, text, but sometimes it's good to actually see what the synthesizer thinks we did. So if you go under Analysis and Synthesis, and I come down under Netlist Viewers, you can go under and you can double click on a thing called RTL View, and it will generate a graphical depiction of what your circuit looks like. So when it's complete, you get to see this image right here. And what this does is it groups all of your logic into blocks that are representative of what's on the FPGA. So you'll notice right here that we have a current state block right here. This is going to be your finite state machine right here. Okay, and then we also see we have a clock divider precision. Over here, we have a read-write memory block right here. These are the names that we had in our prior lab. And then we have a whole bunch of car decoders over here, which are kind of interesting. So anything with an X on here or a plus sign, it can be expanded. So if I wanted to look at my clock divider and see what the tool did, you can actually open it up and you can start seeing some of the logic blocks that were used to implement the logic that we have. So this thing right here, if you scroll down and scroll around, well, if you look at this right here, it had some D flip-flops over here. It had some D flip-flops right here. It had all sorts of multiplexers. And what it ended up doing is it put these all together in order to accomplish the logic that we had written in our VHDL. Okay, so I can subtract or close that down. If I look at a car decoder, it is also kind of interesting because remember that all combinational logic on an FPGA is implemented with lookup tables. And lookup tables are nothing more than multiplexers. So in this situation, you'll notice that I have a 7-bit output of each car decoder. Each bit is a combinational logic circuit, and each bit is implemented with its own multiplexer. And so each 7-segment decoder has 7 multiplexers in it, each representing a combinational logic lookup table. Okay, so that's the actual FPGA implementation of this thing. Okay, so you can kind of poke around and you can see things that are basically natively put together with built-in blocks within the FPGA, and then also ones that are combinations of things. If I open up the read-write memory, what's kind of interesting is that it had a read-write memory block inside of here, and it had just some different inputs, right? So it had data in, but it had a couple different, it had a clock, it had a clear, enable, all sorts of stuff. So it took that built-in block that was already on the FPGA, and it wired it up with some D flip-flops to implement the actual logic that we modeled in our read-write memory. Okay, so if you look at the RTL viewer, and you can zoom in and out by holding the control and kind of scrolling in and out, this is deliverable 3, so go ahead and take a screenshot of that and save that off as deliverable 3. The RTL viewer is good because sometimes you just want to know what the synthesizer thought your design was going to do. So that's a graphical way to look at it. Okay. The fourth deliverable is a way to look at your finite state machine. So remember that in our lab 10.2, we actually had a control finite state machine, and we drew out a state diagram, and then we implemented it with the 3-process model. Well, this is fantastic because you can actually look at the state machine viewer and see how the synthesizer interpreted your VHDL, and it puts it back into a state diagram. So this is really interesting because it sees if you should be able to look at this and immediately see whether or not this is the logic that you're intending. And it actually can come down here and it tries to put the information in like a transition table so you can kind of get more tabular information about the behavior of this finite state machine. You can also look at the encoding. And so you look at how the states were encoded. So what it did is it said, I'm going to have start be encoded as a particular code, and then these other ones will have different codes in them. And so this is a really powerful tool to just double check that you modeled your logic correctly. So go ahead and take a screenshot of that, and that's actually your fourth deliverable. And then the final thing that we like to look at sometimes is our technology mapper. Okay, so the technology map view is where you actually look at the chip and you say, where did everything actually get placed? So the way that you do that is you come down to the chip planner tool. So that's located under the fitter, and then you double click on the chip planner tool. So when this comes up, what you're going to see is kind of a view of the FPGA in terms of its actual resources. Now, it's not down to the transistor level, but it is down to the logic block level. And so when you look at this, you're going to start seeing all these little rectangles, and you can kind of zoom in on them by holding down the control key and scrolling in. And anything that you've used, what's going to happen is it'll be highlighted. So you can see that down here, actually up here too, down here you actually see a block of some of these rectangles that we've used. So if I go take a look at it, I can actually start diving down and seeing the physical resources on the FPGA that I have used. And this is important when it becomes really important when you try to do things like timing analysis, where you really want to know why your circuit is not running as fast as you thought. But let's go ahead and let's look at some of these. First of all, these columns right here, the green are going to be memory, and so you can see that we used one of the memory cells here, and that's to implement our 256-bit memory. These are going to be logic elements. So if you come into here, you can zoom in and you notice that it gives you even finer granularity in terms of what we've used. So I can come into one of these and I can click on it, and if I double click on it, it'll actually show me the specific things that it's used. So if you look at now what I have, I've actually jumped into one of these LABs, or the logic blocks, and inside of it, you start seeing this architecture that we've kind of covered. Now, this is even more detailed than what we looked at in the book, but you can kind of see the core themes emerging here. So number one, over here on the left, you're going to see these highlighted blocks that we've used, this F0, F2, F2. These are lookup tables, and so these are implementing logic functions, and you can see that there's enough information in these, or enough resources in these lookup tables, that you can actually implement two different functions. And this has something to do with the logic that we've created. And so if you come over here and you start looking at what it's implementing, you can come down and you can look at the actual signal names in our VHDL. Notice that within the logic block, also over here are going to be the D flip-flops. So you'll see that there's both combinational logic in terms of lookup tables, there's also D flip-flops, and then there's your multiplexer, which allows you to either be combinational logic only, be D flip-flops only, or be a combination of both. And in this example, we were a combination of both. Okay, so this is a very handy way to look at kind of the resources that we've used. And let's see, so then if we kind of scroll out, you can kind of see some of these other ones. This is another block that you can see here. And they all look the same, you know, it's an FPGA, so this is kind of how FPGAs are. It's just an array of consistent logic. Let's take a look at what happens if I look at the memory and see if it gives me any information. So it has this kind of block diagram level view of what we did with our memory, and you know, it just has this little block that's got 32 by 8 bits in it. It calls it a simple dual port memory, and that's the resource that we're actually using. Okay, so once again, a very detailed view of the actual implementation of our circuit on this specific FPGA. Okay, so what we want to do for deliverable number 5 is open up one of these LABs, or this view where you're actually seeing the actual logic block itself, and go ahead and take a screenshot of that for deliverable number 5. And that wraps up this lab. And so hopefully this kind of showed you some of the tools that we have available within the synthesizer tool Quartus, and some of the things that you will want to look at as you try to design more, you know, digital systems that are more complex and that need to meet both, you know, size constraints and timing constraints. Okay, so that is lab 11.1.